There we go. So we have the last talk for this workshop. Scott Lawrence is going to talk about convexity and quantum fields.
Thank you, Sri. Thanks for letting me speak here. So this is a somewhat algorithmic talk. The algorithm is focused on defining a convex space and then doing convex optimization. I'm going to start off for the first half of the talk, rather than talking much about algorithms, just sort of reviewing very pedantically how it is that convex optimization naturally comes up in quantum mechanics and quantum field theory. And so this is based chiefly on a couple papers over the last 2 years, applying the methods in this talk to lattice field theories, which I'll get to at the end. And I apologize to those of you who've seen this talk before, which is now getting to be a substantial fraction. It's worse and worse. Soon it'll be 100%. Okay, so this is just sort of a review of the ingredients of quantum mechanics. At risk of putting people to sleep, you have a vector space of, well, a numbered space, but I don't care, right? A vector space of states. You have an inner product which has to be positive semi-definite, a collection of Hermitian observables, one of which is the all-important Hamiltonian generating time evolution. And one of the states is now singled out as special because it's the ground state, the lowest line eigenstate of the Hamiltonian. For the purposes of this talk, one of these ingredients is unusual. It's this inequality, the fact that the inner product has to be positive semi-definite, but we know nothing other than it has to be greater than or equal to 0. Or on a given state, it could be any number that is not negative. And so we can use this to prove bounds. If you want to prove that something in quantum mechanics is greater than or equal to something else, chances are you're going to have to use the only inequality that appears in the axioms. So we could ask for bounds on ground state properties or thermal behavior or time-dependent behavior. The easiest one is to get bounds on ground state properties. That's what this talk is about. It's repeatedly apply the fact that the inner product is positive semi-definite to discover something about what the ground state, and then at the very end, low-lying states look like. So there's like a trivial example that you probably all saw in Quantum Mechanics 1. Just to review it, we start with the harmonic oscillator, and you could actually solve this, but that might be a little bit time-consuming. So rather than doing that, just remember that for any state, no matter what state I'm talking about, the inner product has to be, the norm has to be non-negative. So let's take the ground state, whatever it is. I don't know, I don't have to tell you, but take it, you know it exists, hit it with x. That's a state whose norm is non-negative. So we know that the expectation value of x squared is non-negative. Ditto for p, and now we learn that the Hamiltonian can never be negative in the harmonic oscillator. Of course, this isn't a tight bound. We all know this isn't a tight bound. Really, what I should do is consider a slightly different state. So take the ground state and hit it with x plus IP, the ladder operator, in other words. And now this is a state whose norm has to be non-negative, but that results in a dagger A having non-negative norm. And that leads to this uncertainty principle bound that the expectation value of the Hamiltonian has to be greater than or equal to 1/2. Okay, and we've all seen this. In the case of the harmonic oscillator, of course, this is the tight bound. This is the solution for the ground state. Okay, another example to beat this to death, if I do one spin. So here the Hamiltonian is just sigma x without loss of generality. For our state, we'll take 1 minus sigma x times, again, whatever the ground state is. And so we get that the expectation value of about 1 minus sigma x has to be non-negative. And as a result, the expectation value of the Hamiltonian is bounded above and below by minus 1 and 1. Same idea. In both cases, the bounds are tight, and this is just essentially because we're able to exactly solve the theory, right? I'm giving you a sketch of the solution of the theory with some unnecessary steps taken out. So let's do this a little bit more systematically. So far, I've been describing this procedure where I specify a state and then I obtain another state, and it's a bit hairy. But we can just say that, look, in the ground state for any operator O, the expectation value of O dagger O has to be non-negative. So as a result, if I take a basis of operators, not a complete basis, that might not be possible, but some basis of operators O1 through On, and I construct a matrix of expectation values, O dagger sub I times O sub j, expectation value, that matrix has to be positive semi-definite. So you can phrase this if you want as any eigenvalue of that matrix has to be non-negative, or you can say that for any vector, if I take the inner product of that vector through the matrix, that has to be non-negative. These are all equivalent. They follow directly from this positive semi-definiteness constraint. In fact, not only that, but if I've included a complete basis of operators in constructing this matrix, then this is the entire positive semi-definiteness constraint. So the whole thing is summed up in this slide. And then if I use that, then I have used all inequalities available to me in the axioms of whatever quantum mechanical system I'm looking at. You know?
Wait, I have a stupid question. That matrix M just looks Hermitian to me. So is it more than Hermitian?
It wasn't Hermitian. Yeah, wasn't a stupid question. It's more than Hermitian, it's positive semi-definite. It wouldn't be for general vector space. Sorry, it wouldn't be for general bilinear, right? It's true because the norm of the vector space. Okay. So this is a special case. How is this going to turn into an algorithm? Well, this is a special case of something called a semi-definite program. And the story here is that the space of matrices that are positive semi-definite is convex. So I can, if I have some linear function on this space, I can minimize or maximize. In this case, I'll always say minimize, okay, for convention. So if I have a linear function on the space of positive semi-definite matrices, I can minimize it efficiently. It's a convex optimization problem. And that's what a semi-definite program is. So sort of very concretely, let C be some n by n matrix. It represents the Hamiltonian. We're going to find a positive semi-definite matrix X. That's the matrix of expectation values, which minimizes the trace of Cx. The trace of Cx is sort of like the most general linear function you can define on this space, subject to some linear constraints on the matrix elements of X. Okay, so C is the Hamiltonian, and the linear constraints come from the commutation relations. The most obvious one being that xp is px plus I, and so their expectation values can be related accordingly. It is a very fortunate thing for us that imposing commutation relations yields linear constraints. You can convince yourself quickly that this has to be true, but this preserves the fact that we're taking a linear slice of the big space of semi-definite matrices. The fact that we're taking a linear slice of that space makes it so that we're still minimizing over a convex space. If I were to add an extra step here, and I'm going to harp on this a lot this fall. If I were to add an extra step down here, where I had some arbitrary nonlinear constraint, then in general the space would no longer be convex and it would be difficult to perform the optimization. Okay. So one spin again. So here actually just write down a complete basis of operators, because in this case we can, there aren't a lot. And this matrix has to be positive semi-definite. That's the full positivity axiom. In fact, any assignment of expectation values to this matrix that obeys positivity corresponds to some density matrix. You can go back and forth if you want. If you want, you can think of this whole talk as working with density matrices in some weird basis. Of course, to deal with this Hamiltonian, you only really need the upper left 2x2 minor right there, and you recover the usual result just by taking the shortcut of looking at the data. So far, nothing exotic has happened. This is just to visualize what's going on when we perform the minimization of the Hamiltonian. So the space of allowed matrices has one parameter only, because we're looking at the upper left minor. So it corresponds to a convex space that is just the interval between -1 and 1. And then if you plot the expectation value of the Hamiltonian, then the shaded region, the region that's sort of accessible, is again a convex space. And you just minimize, you sort of imagine dropping a ball here and letting it roll down. That's how to do convex optimization. Obviously, real convex optimizers is much more complicated, but you can at least convince yourself that this is a problem. Harmonic oscillator, really beating it to death here. You can't use a complete basis. That's the novel thing. But for the harmonic oscillator, I can just use X and P and the identity operator. This matrix has to be positive semi-definite. The lower 2 by 2 minor turns out to be the only thing you need. And again, imposing that the determinant is non-negative, you recover now. In fact, you recover exactly the usual way of writing the uncertainty principle, which is equivalent to the lower bound on the ground state. If you add more operators to this matrix, so this isn't a complete basis, if you add more operators, this can only make the bound stricter. So for as long as I'm just going to talk about, here's a bound on the ground state energy, this is a true lower bound. You can think of this if you want as dual to the variational term, right? When you're doing a variational calculation, you write down some ansatz for your wave function, and you try to minimize the energy of that wave function. You say, well, at least, if I want to be rigorous, at least this is an upper bound for the ground state energy. This gives you a lower bound. If you combine the two, you get, you can sandwich them. In principle, you might be unlucky. It might be a very big thing. Okay. One other alternative viewpoint, we can call the whole procedure non-commutative sum of squares. So far I've talked about, write down a big matrix and minimize in some space. You can also view it as, look, my task is to write the Hamiltonian in a form like A dagger A. Right? That's how we usually do it in quantum 1. If you want to solve the harmonic oscillator, you know that the Hamiltonian has the form A dagger A plus a constant. You say, well, A dagger A is manifestly positive semi-definite, so that constant must be my lower bound. And so this, what I've described, the semi-definite program I've described, is dual to a different task where you try to do exactly that. You try to decompose your Hamiltonian in a form O dagger 101 plus, a sum of similar terms, and then finally plus a constant. And the largest constant you can get there is your type bound. All right, so to sum up, the space of permitted expectation values is convex. The ground state sits at the boundary of that space, and it can be obtained by writing down the Hamiltonian, which in this space is just a linear function, and minimizing the Hamiltonian. You hit the ground state as you sort of roll downhill. You could do either sum of squares or solving a truncated SPP, semi-definite program. And so for the rest of this talk, I'll first give a little bit of history and context on the conformal bootstrap, to which this is all closely related, bearing in mind that I'm not an expert in it, but I would be silly not to mention it, given how closely related it is and how successful the conformal bootstrap is. And then I'll discuss the computational application of this to lattice systems, and finally at the end, how to understand the low-lying states for this method. And I've beat this to death enough, you guys get the point. Okay, so the history here is that once upon a time, several decades ago, there was this dream of constructing an S matrix purely by saying, well, here are the symmetries and here are the consistency conditions that an S matrix must obey in order to define a good QFT. And at one point it was hoped, maybe there's going to be one QFT. Maybe if I demand full consistency of my S matrix, there won't be a lot of freedom and we'll know what quantum field theory we're in. That never happened, of course. And in fact, the whole method pretty much died down as modern quantum field theory developed and QCD became understood. And then about a decade ago, there was modern numerical techniques allowed one to write down essentially a large semi-definite program and solve it. And so there were good reviews, I think, but various one may do, but I'm not going to remember all the authors. So. But about a decade ago, managed to do this and obtained rigorous bounds on the Ising model, and as a result, sort of Bootstrap, which refers to this program, and semi-definite programming are now somewhat synonymous. So, sort of a review of what a conformal field theory is. You have all these various constraints, but a key one is that there's this inequality coming from radial quantization, and again imposing positive semi-definiteness of an inner product. That corresponds to unitarity. But then you have a bunch of equalities, just like in the quantum mechanical case, we have the commutation relations. In the conformal case, you have whatever symmetries you've proposed, which is quite a lengthy list of conformal invariants, and crossing symmetry as well. Okay, and there's a good canonical review. So that has roughly the same structure. I should also mention for the purposes of this workshop that of course you can also perform the conformal bootstrap in the presence of a boundary or a defect, adding to your crossing equations the operators that live on the boundary or on the defect. And so this has been done, I mean, very recently from, line defects in an O3CFT, but it was developed roughly at the same time as the original formal bootstrap. Okay. So this talk, however, is mostly about the quantum-mechanical bootstrap. And so the ingredients here, as we've discussed, right, you have a Hamiltonian, some operators, and the commutation relations. You minimize the Hamiltonian, which is equivalent to solving the semi-definite program. The history of this one, it was revived a couple years ago, but it turns out that this was first done in 2011. So Barthel and Hubbiner applied this to the Hubbard model with some success, and then sort of nobody followed up on it for a decade. In part, I suspect, because the tools for solving semi-definite programs were not quite as well developed 12 years ago. But then this was substantially expanded 2 years ago now, by Berenstein and Halsey to various quantum mechanical systems. I should note, this is a very biased talk. So in this talk, I'm very careful to always be doing a convex optimization problem. If you're willing to put the blood, sweat, and tears in, you can do it otherwise. You can sort of say, well, I have a minimization task, it's not quite convex, but I'll work really hard at it and make sure that I'm sure I found the global minimum. Okay, and that's an approach often taken. I won't do that. At every step in this talk, I'm going to make sure that I'm only doing convex optimization, because that's already enough. That's already painful enough for me. Okay, so now let me demonstrate, we've discussed this for simple quantum mechanical systems, and that's what Berenstein and Halsey did. Of course, from a certain point of view, a lattice field theory is a simple quantum mechanical system. It just has a few more degrees of freedom than you were expecting. So let's do that with scalar field theory, right? A bunch of harmonic oscillators, well, a bunch of anharmonic oscillators coupled like so. Here's the coupling term. This is just P at a site. And what in field theory we would call the coupling term, but here's just how anharmonic the oscillator is. And what I've shown here in this plot is a Monte Carlo calculation. This is all done at infinite volume. The Monte Carlo calculation is just done at large enough volume that you can't tell it's not an infinite volume. But solving the semi-definite program, you can do directly at infinite volume due to the fact that we're only working with operators, never directly with the Hilbert space. So the Monte Carlo points, and then various estimates on the ground state energy density from solving increasingly large semi-definite programs. Okay, I've put the basis of operators up here on the left. And the point here is that, particularly if you're sitting in the back, the last two semi-definite programs lie directly on top of each other. They differ by a small fraction of a percent, and they're both compatible with Monte Carlo results. So we've recovered. Now, full disclosure, like this is not impressive, because the Monte Carlo ran faster than solving the semi-definite program. Okay, it did that because this is a theory. It's one of the special theories for which there is a very efficient Monte Carlo.
What is that plot?
What's being plotted?
Yeah.
Energy density.
Energy density per what is the
Per unit. Coupling. Sorry, yeah, coupling constant. So on the left you have the free theory. I should mention, because this is kind of interesting. So when you do a truncated SVP, you've done some approximation. It is not an easy to understand approximation. I don't have a way to efficiently characterize it. So in particular, it's not perturbation theory. You can see that quite clearly from the fact that these truncations don't match even at the free theory if you take a low truncation. In fact, none of these truncations, no matter how high you go in L and N, will exactly match the free theory. Okay, they'll get exponentially close in L, but that's it.
So does it seem like any particular operator is more important than another? Like, is a 5 to the 4 operator a really good thing to?
Some operators, yes. So some operators end up being better things to add to your basis than others. Because you're not going to like the next comments. Yes, and check. Hopefully someday that's not the answer, right? But right now, genuinely, I have a footnote somewhere here for there's an automated guess and check procedure.
just make sure. So here the pi and the pi side of the sum commute.
Yeah. They made the same commutation relations if they're at the same site as X and P. If they're at different sites, they commute because this is the boson up there. But this is boring because I can compute that anyway. In fact, it's easier to get the Monte Carlo. Okay, so finite density fermions, right? This was always going to end up here. We're all familiar with the story. For me personally, the most interesting thing is dense nuclear matter. But you know, also relevant if you want large nuclei, also relevant if you want to look at superconductors. And you know, very relevant if you want to add your own curve to this plot. So well, or you can make something up, I guess. So let's do this at finite fermion density. The punchline is going to be that it performs as well as it does for scalar filter. Its performance properties aren't perfect. You know, it's not a statistical estimate. It's some bound. It's a very difficult to control approximation, but it does about as well. It doesn't suffer from anything that looks like a fermion sign problem. So here's a lattice tiering model. I've used staggered fermions, chi dagger into chi, with commutation defined there. Nothing here is very surprising. There is, of course, a chemical potential. And so in this plot, yeah, I apologize for the fact that the x-axis label is tiny, but the x-axis here is chemical potential, good. And the y-axis is a shifted version of the energy, which is related to the integral particle number as a function of chemical potential. Turns out this is a thing you can bound. And so the exact result is the highest result, the solid black line, and various semi-definite programming bounds approach that line and bound it from below. And you can see, in fact, as you lift the truncation in the semi-definite program, you get better and better results at large chemical potential in particular. You exactly reproduce the line at large chemical potential, and at small chemical potentials, you do well, but it's not an exact reproduction anymore. And this is designed to be at, I picked the massive coupling carefully so that this is at strong H coupling, where there's a bound state which of two fermions, which is about equal in mass to this to massive one fermion.
Do you have any intuition for why it's better at large mu?
I think so. I think near lattice saturation, correlation lengths become very short. And certainly all the way at saturation that happens. And the semi-definite program does very well in correlation lengths. I think that's part of it. The theory does that all the way at saturation, you know, the theory trivializes. You don't have coupling between the different sites. And that's the thing, you know, no matter what truncation you pick, you always reproduce this, the final bit of the line down here. And so that's related to the trivialization of the theory at saturation chemical potential. Why exactly the whole thing comes up here rather than doing something more interesting here, I'm not quite sure.
And the flip side of some of what you said is that if you do have a large correlation length, there would be some
There's
challenges.
a slide for that a bit later. But yeah. It's a polynomial size problem in the correlation length, but it's a bit of a steeper polynomial than the usual one. Yeah, lattice parameters there. Okay.
So how long are these calculations typically take?
Well, the length of like to produce this plot, I think for the whole plot it was about an hour. There's a pretty dense sampling of points in there as well. However, in practice, the limiting factor has been the amount of memory that's used. So this is there are comments scattered throughout these slides. I'm trying to resist the urge to rant about this, about the state of semi-definite programmers, semi-definite program solvers as software. A lot of the time you'll have a semi-definite program, you pass it to 3 different solvers and you get 3 different answers. And the one I use a Bozek, which is some commercial thing that you can get for free with an EDU email address. It has strange performance properties and it uses way more memory than it should. And so that's the limiting factor, not so much the time.
So when you say you get different answers, there's a unique correct answer.
There's a unique correct
Okay,
answer.
so some of them are just wrong, you're saying. Some of them.
Almost all of them are just wrong. Well, they're the ones that never terminate.
So wait, so to make this matrix of operator expectation values, don't you have to do a Monte Carlo to make that matrix? Because it's averages of operators.
I don't make that matrix. So what the semi-definite program solve, what the SDP solver is doing is it stores a matrix where it just made up some numbers, and then it changes those numbers in a way consistent. So the Hamiltonian, remember, is just some linear combination of those. It changes those numbers in a way consistent with the positivity constraint to minimize the Hamiltonian. So at no point do I honestly calculate an expectation value. I did honestly calculate expectation value. It's much easier. Okay.
Also,
Yeah. Oh, more questions.
yeah, I did maybe understand, but did you choose the, let's say, operators?
Yeah, I choose them.
And how do you, so,
I didn't put them on this slide.
and you need to choose for, to give some boundary that you want to, look at it. You mean, so, I mean, if you show some plots in the previous slide.
Yeah.
So you want to, you are interested in this y-axis.
Each of these, yeah, so exactly. So I'm interested in the bound on the y-axis, which is bound on the energy essentially.
I see.
And each of these lines corresponds to a different choice of
I see.
operator bases. And they're getting larger. So what I call H1 includes H0, what I call H2 includes H1, and what I call C1 includes H2.
I see. So you know the operator combination of operators such that you
Getting
can
those
look at
numbers.
that.
Yeah.
Oh, is it easy?
No.
Okay.
I mean, it's, so I'll show you, I'll just make the point.
Okay, yeah.
We can look at the operators. And they look very reasonable. So H0 has C dagger C and C dagger C at every side. That's what you need in order to get any bound on the Hamiltonian at all. Because of course you have to be able to construct the operators in the Hamiltonian from your basis or from products of your basis. So this is the minimum thing you can do. And then you look at the Hamiltonian and you add things you see. You say, well, I see a kinetic term, I'll add that. Okay, great. That gives you H1. You say, I see this 4 Fermi coupling term, I'll add that. That gives you H2. Then you say, what do I do? Well, you guess and check. And it turns out that the only operator that gives you a non-trivial bound at this point is C dagger and C at 2 different sites times on a third site the number operator. Okay, I would not have guessed that.
Are there any constraints from symmetry, for example, like that? For example, you need to add the terms such as, how to say, terms which.
You can use a basis that does not respect your symmetries. It's perfectly okay to do that. It's still a lower bound. The question you might want to ask as well, do I do better if I include the full symmetric set? In general, I think the answer is no. So for instance, I think I did not include in the C1 calculation, I did not include the reflected version of that. And in fact, it doesn't help that much. Okay, and there's a greedy algorithm, which is just more professional guess and check. Yeah, oh yes, sorry.
I have 2 questions. Why is C dagger C not the minimum set? Why do you have to have C dagger C? Sorry, C dagger comma C. Why?
Yeah, because there's a coupling term, which is C dagger C, and your matrix is only constructed of O dagger O with O in your basis. So in order to get the coupling term, which has 4 operators, you need something in your basis that has 2 operators.
I see.
Second question.
So the products are, yeah, you're only gonna get 2 sort of square terms in there.
Yeah, if you have only, so if you choose only C dagger and C, you can solve the free theory. And in fact, in general, like a way to solve the free theory is to write down the semi-definite program consisting of only single operators.
Okay, second question is, do you have a sense of scaling with system size?
Not a good sense. There are 2 questions here. One is if I sort of fix the type of basis I've chosen, like I fix the truncation and I increase the system size, everything scale. The answer there is, in principle, never mind what the actual solvers do, since half the time they fail to terminate. In principle, it's the most of the time is spent doing matrix operations. And if you have a basis of k operators, you have a k by k matrix, so you expect it to be somewhere between k squared and k cubed. Okay, and then a small k dependent factor to account for the fact that you have to take multiple minimization steps. But that's for a fixed basis, and then there's the question of, well, how well does that basis perform as I increase the size of the system? I'll touch on that for the free theory on a slightly later slide. But in general, no, I don't have a good answer. Okay, more results for the same thing, which we may as well skip. I did promise you guys a discussion of what happens for the free theory. And this also doubles as we have to the point that we can do these calculations at infinite volume, because I just have to pick a set of operators that's at finite volume, but the Hilbert space itself is only at infinite volume. So here we're going to minimize the Hamiltonian density. And what I've shown is, so the exact results for 3 different lattice masses for the number density at some value of the chemical potential versus a few different semi-definite programs with increasing L. So I included operator space at any point X between -L and L+1. Okay, so in other words, I'm including operators in my basis that are increasingly spread out. So the operator spans some non-trivial volume in my system. And you have to do this in order to capture some of the long correlation length. And so what you see is the longer L gets, L is on the x-axis. The longer L gets, the better all of the semi-definite programs do. But you do much better. It's a little hard to read this because as you increase L, it's a bit noisy.
So y-axis is error, what do you want?
Y-axis is error here, yes,
From the exact result.
from the exact result, yeah. Because this is the free theory. What happens is that for the larger mass, where the correlation length is shorter, you do much better, much faster. Y-axis is log scale, by the way, in case it looks really bad. You do much better, much faster. When you work with the smaller mass theories, the decay is much more gradual, because of course what matters isn't L, what matters is L. The correlation length.
Why is the exact result independent of L? Or are you just plotting the?
It's the infinite volume exact result. These calculations are all done in infinite volume.
The fact that it extends for general L is just to guide the I.
Yes, yeah, it's the guy that, that's it.
I thought L.
The SDP calculations are also done at infinite volume, to be clear.
And what's
So it is
actually-
appropriate to compare this blue point to this blue line. I don't know if that was.
You have L on your plot, so.
I don't know. It is I'm working at infinite volume with a basis defined by finite L. So I have a finite basis, the operators in that only span up to a certain distance, but the bounds obtained on the energy are accurate are true bounds in the infinite volume.
See, L here has nothing to do with the volume. L has to do, I see.
It has to be actually to do with the volume, because it's a sort of finite volume effect, right?
Okay,
But then,
now I get it, thank you.
So the product, the operators that you're including which have support over this L sites, are they like products, like, you know, a product?
but it's the free theory, so I can get away with more.
Just to point.
That's a little bit. So everything I've talked about so far has been getting at ground state physics. You can estimate expectation values, you can get bounds on the ground state energy or energy density. And this is sufficient if you want an equation of state. This is sufficient if you secretly want to do relativistic physics, where the correlation functions in the vacuum tell you quite a lot about excited states. But for non-relativistic physics, that's not as true. So I might want to ask, what are the low-lying excitations? If I have a certain very small energy budget, which operators can I excite? And I want to do this while preserving convexity. I'm going to die on this hill, right? So we have access to the ground state. I want low-lying excitations while preserving convexity. How to access finite temperature is not well understood right now. This is a bit of a lie, but we'll pretend it's completely true that I don't have any way to access finite temperature. So what I can do is I can calculate the ground state energy, or at least the SDP estimate of it. And I can add a linear constraint. I can say, you know what? I'm only interested in the space of density matrices where the expectation value of the Hamiltonian is equal to whatever ground state energy I've estimated plus a small boost set at will. Now I'm talking about density matrix that consists of ground state plus some low-lying excitation, right? Because I don't have enough energy to talk about any high mass modes or anything like that. And now I can minimize or maximize, not the Hamiltonian. If I fix the Hamiltonian, that's a really boring minimization problem. I can minimize or maximize any other expectation value of interest. So what I'm asking is, if I restrict myself to an extra bit of energy delta, what operators can I excite? Okay. Any bound obtained this way, so I'm going to minimize or maximize an expectation value. You say, oh, that's a bound. It's not really, because I've added this E naught isn't the true bound state energy. The true bound state energy, in fact, this is likely to be larger than E naught plus delta. What this is actually going to give is a qualitative hint as to the physics of the system, not a rigorous bound or anything like that. But sometimes, that's good enough. So just as a very simple demonstration of this, so if we look at the Kitaev chain, so here, we have we have one parameter in this system, but there's mu and there's t, and the mu is much larger than t. We're in the same phase as a sort of trivial tensor product system. And when t, there may be a typo here. At In the other limit, there are Majorana edge modes. And what I plotted is as a function of, for 20-site lattice, for 20-site chain, I have plotted as a function of the chain position, the maximum expectation value of the Majorana at that site for 3 different sets of the parameters. So you can see in the dotted line, the mu is much larger. There's nothing exciting happening at the edges. If I restrict myself to low energies, then all expectation values change together. Nothing strange happens. But as I take t to be larger, you can see that in fact you have these low energy excitations that are now available on the edges of the chain. And in fact, not only can you see that, but at intermediate t over mu, you can see that these edge excitations are also spread out. They go some finite depth into the chain from the edges. So with that, that's all. And then you can do the same thing if you like, adding an interaction. The plot is much harder to read and interpret here. I suspect this is partly because I chose my interaction strength for it. But this is just to make the point that this plot, you can, it's a free theory, right? So you can get this plot analytically, essentially. But working with the semi-definite program, we can also just add an interaction and work in the same approximation or an improved approximation and get some qualitative information about edge modes. And at least you can see there are still edge modes when I add the interaction. With that, there are various references you may find interesting. Thank you.
How can you learn the local, configuration from your program?
How do I learn the local?
No, I mean, the next previous slide, yeah, this one.
Oh, this.
Yeah, and yeah, you can learn the,
You're asking how it is that there's something plotted over.
yeah,
Right. So what I'm no longer minimizing the Hamiltonian. So I fixed the Hamiltonian expectation value. So it's a boring thing to minimize. And I said, I'll pick some other operator to minimize. In this case, I chose expectation values of a Majorana at a site. So what's plotted here is the maximum value at low energy of the Majorana at the very edge of the chain, and so on. Right. And in fact, there's a completely massless mode. You could, by the way, if you wanted, you could pick other operators, right? It should be possible to do a similar trick to see like a chiral current around the edge.
so you use the opposite logic.
Exactly. And the price you pay is that now this is a much more difficult to understand approximation than what we had before, where at least I could say, well, it's a lower bound. Now I can't say that anymore. I mean, I could, but it'd be a lot.
Isn't there any, how to say, error bar or something on these plot? No.
The only way I know to get error bars is to work with different. Let me just show. So here we go, right? To work with different truncations and sort of do it by eye, right? If you didn't have the exact line here, you could still look at the fact that these couple bootstrap calculations seem to have converged, and so you could guess that the error bars are small. Of course, you'd be wrong. Because you'd also say the error bars are small here, and they're not. The exact thing's right up there. Not a very reliable.
So you mean there's some error bar for determining the ground state, but if you calculate some local, the last lines, then there's no error.
For determining the ground state energy, you have a lower bound,
Yeah. So
but
it's
no reliable error bars.
I see.
And for everything else, you just have nothing. It's like it really is doomed to variational patterns, right?
So what is your conclusion about this whole technique, especially since you're doing 1D systems here, which is dangerous because you always have to compete with the MRG.
Right. It has been demonstrated on 2D systems. It doesn't perform dramatically differently, but you have a much larger basis of operators you have to work with. And so you end up forming much substantially larger complex optimizations. My feeling about this method right now, I think I have a slide at the end with some data for it. Yeah. My feeling about this right now is that the main obstacle is the lack of better tooling for solving large SDPs. And I am somewhat vindicated in this. The conformal bootstrap people had to just go and write their own SDP site. That one's difficult to use for these purposes. It's very specialized. But that was the state of 8 years ago that Poland, I think, and some Dublin and their own. And it's likely that that's where this is going as well. The properties of the SPK solver we need are different, so they needed multi-precision arithmetic. All the evidence for reasons I don't understand, all the evidence for lattice field theories is that precision isn't the problem, just the sheer number of operators is. I think that's the obstacle of the 2+1. It's like large 2+, obviously, you know, the very first result was a 2+1 system, it was the Hubbard model.
Right, so you think, as in, do you think that it would be able to compete with DMRG in 1D, or do you think that the main draw of it is that it is easily extendable to higher dimensions?
The main draw is that it doesn't suck at higher dimensions. I don't know about competing with DMRG in 1D, but I've never really considered that. I view 1D systems as DMRG is good enough. Yeah, so I wouldn't be spending all my time on if the draw was beat DMRG, which is already kind of unfair. It's not, you know.
Can you study a system with time problem?
Yeah, that was the point. This I think has a sign problem, but also this definitely has a sign problem. This is like a classic sign problem system to study, right? So I've done this with Monte Carlos.
So this is 1D, right? That's what DMRG.
Yeah, but and I think this also has one flavor in it, so it might be. I think this formula is one. You don't even need DMRG.
So in principle, we always have this QCD phase diagram where no one knows what's happening. In principle, can you then just, you know, just do this?
It's simple, yeah.
Yeah.
But you know, you go into a little estimate of the size of the semi-definite program you're gonna work with.
Yeah.
I think for like a small QCD lattice, if you just work out the naive scale of how much memory should it require, it's doable, but no currently existing tool can do it.
Okay, but it's doable, meaning it's, you don't need to build a.
As far as I know, I don't know. For like small, you know, we're not gonna do 20 by 20 by 20, but even a 6 by 6 by 6 thing in the vacuum would be fantastic.
And you hinted that there's a problem, space transition with the correlation diverges.
Yeah.
Can you check critical exponents and things like that?
No, that's exactly the point. So, okay. If you try, I don't remember if it was 1D or 2D, some easing like model I tried extracting, and you get if you just want to, never mind critical exponents, if you just want to see where the critical coupling is by plotting the susceptibility, you're substantially off, like 20 or 30% off consistently, because of course you are. You have to have a huge basis in order to accurately be reproducing that. So that's the region where this was first. It may be like the cleverer choice of basis, you can read that down.
The worry would be that in QCD at high density or at even moderate density, it's very number spontaneous broken, correlation is infinite. And
Yeah, well, I mean, I care about the correlation life on the lattice, so it's also taking the continuum limit before I get to worrying about phonons of spontaneous breakage.
but if you want ground state properties, then then call it limited and continuum, then but we're very far from that.
I mean, the same thing would be, I mean, again, it's a polynomial thing in this case, and it would be a polynomial thing on the lattice. If we solve the fermion sign problem on the Euclidean lattice, we again would have to cry about that issue.
Actually, on that note, this is all purely quantum Hamiltonian formulation, right? There is no.
Okay, yes, good. Yeah, so you're gonna ask about Euclidean, right?
Yeah.
Hang on, there's a thing here. Here we go, easing. This is gonna say easing somewhere, right? Yeah, this paper. So they do something, I mean, it's the classical easing model, but effectively it's the Euclidean form, they do various exotic lattices. Effectively, it's the Euclidean formulation of the transverse easing model. So essentially what happens here is you say, I'm not working with a Hilbert space, I'm not working with a positive norm, I'm working with its replacement in Euclidean space, which is reflection positivity. And then everything goes through without change, except now you have an extra dimension. So you are paying the cost of a much larger basis. On the other hand, you no longer get a lower bound on the Hamiltonian, you get lower and upper bounds on any operator you care about, right? So you could get a lower and upper bound on number density and arbitrary chemical potential. The price you pay is a way larger SPP, which is outside of the range of things we can do about that. Back to my ranting about that.
You mentioned the variational principle as a complementary, so you could go from above. variational principle allows you also to access the excited states relatively consistently by essentially eliminating the base of the ground state. Is there a way of minimizing for the energy of the first, second, and so on excited states here?
I think so. I haven't looked at this too much. I mean, I think it's sort of the same principle. But I haven't looked at this too much because, you know, if your estimate for the ground state energy was far off, then now what you have for the first excited state isn't bound anymore. Right, it's now, because the ground state energy could have been much lower, so your estimate for the first excited state could have had now a lot of contamination from the true ground state. And so you can no longer get around at all, and it sort of feels less well controlled. That's why I looked at it.
Well, they have the Hilbert space and they could go into sort of perpendicular direction of the Hilbert space. So here you don't have that.
But it's perfect. What's it perpendicular to?
Well, orthogonal stage to the ground state,
To the estimated ground state.
the estimated ground
Right,
state.
that's the problem I'm talking about. Is that if the true ground state is far off.
But you're not working with a good Hilbert space, so how can you even define that? That's my question, sir.
Yeah, I see what you mean. I'm sorry, I used to know the answer to this. You go back to the very beginning, I think. You can phrase this whole procedure in terms of working with, not with working with expectation values in a fixed state, but actually working with states explicitly. Right, so here we said, I'll be choosing a bunch of states to work with, and those states will be constructed from my ground state. So if you want to get information about the first excited state, then you construct states not just by hitting the ground state with operators, but by hitting both the ground state and the first excited state with operators, and then considering inner products between the two. And that's the sort of thing that gives you balance. But I haven't, I know nothing published on this. I haven't worked on it seriously. But I think in principle that is a possible thing, and it's spiritually similar to the variation.